The next topic in your syllabus is topic 7, nuclear and particle physics. Okay, topic 7, nuclear and particle physics. And because there is a lot of material associated with this topic, I'm gonna break this down into a series of videos, starting with the nuclear physics part of this topic. So here we will study a little bit of the history of how we came to discover that the atom contains a nucleus and so on and so forth. So let's get started. So nuclear physics, and this is a topic dear to my heart because this is what I got my PhD on. So nuclear physics studies the structure of the nucleus of atoms. Now, what's different about particle physics? What's different between nuclear and particle physics? Particle physics studies the structure of fundamental particles or subatomic particles such as protons and neutrons. Subatomic particles, protons and neutrons. And all these particles are used to build all matter in the universe, okay? So if we are to draw a scheme, let's denote protons with a closed circle. And I wrote the plus because protons have a positive charge equal to plus E, where E is the fundamental charge of one electron, which is 1.6 times 10 to the negative 19 coulombs. It's negative for an electron, positive for a proton. So this is the nucleus of helium-4 pretty much, okay? And here are the electrons, they are point particles, okay, orbiting helium. So this is the atom. So if this is the atom is studied by atomic physics mostly, okay? If we take the nucleus itself, this is what's studied by nuclear physics. Okay, so that's the nucleus. And then if we take one proton, it consists of quarks and gluons. We will talk a little bit about these things. And these are particles. Okay, so this is the big picture. And even though this is gonna go a little bit outside the material that you need to know, I think it's important to go over the history, the brief history of how we came to understand the atom and the nucleus, okay? And I'm having my coffee, so I'm gonna take a sip. So, brief history. As a Greek, I couldn't resist to include 400 BC, where Democritus, a Greek philosopher, contemplated. So Democritus contemplates there must be an atom. An atom is a Greek word. It means something that cannot be cut, so indivisible. So he theorized out of thin air pretty much. So there was an effort back then to describe the universe without the intervention of gods and spirits and such. So he contemplated that if we keep cutting down matter, eventually we'll go down to something that cannot be cut any further. So that's why it's called an atom. and but he had no grounds for that. Okay, then we move to 1803 and we find AD. Okay, so more than 2000 years later, Dalton, a chemist, okay, not a physicist, a chemist, figures, oops, ran out of space, I'm sorry, I'm gonna write here, so figures atoms exist that have different masses and different masses are spherical and are different for different species, for different types of atoms, if that makes any sense, and are different for different types, let's say, types of atoms. And then he hypothesized that atoms combine to form molecules. So he pretty much came up with the idea that atoms are spheres, so the sphere for oxygen is different than the sphere for hydrogen, and these atoms combine between them to form molecules. Okay, so he was pretty much right. Okay, so he came up with that 100 years before physicists, pretty much. Okay, okay, of course we know that atoms are not completely spherical, etc., but he was almost spot on. Okay, then we go to 1906. Okay, and this is something that you need to know a little bit about. 1906 AD, we find Thomson, a physicist now. He hypothesized that the atom is a blob, a positively charged blob. So it looks like a pudding. That's why it's called the plum pudding model. A pudding with positive charge. Sprinkled, kind of, on top. By the way, for the Dalton atom, he pretty much hypothesized that maybe this is hydrogen, this is oxygen, a bigger atom, this is helium, etc. So this is what Dalton hypothesized. Now let's go back to Thomson. So sprinkled on top of this pudding, this positive pudding, this positively charged pudding, are the electrons. So he pretty much figured that the atom should look something like this. So you have your positively charged pudding, okay? It has no specific shape. It's kind of like a blob, like it's not spherical, it's nothing, okay? So this whole thing is positively charged, and sprinkled on top of this thing are electrons, okay? So these are my electrons. And the electrons are points. Maybe I shouldn't put crosses, maybe I should put points, okay? So these are the points, okay? So something like this, okay? So you have a pudding, and on top of that, like the plums on a pudding, okay? The electrons look like plums on a pudding, okay? And then a few years later, a guy comes around at the University of Manchester, I think he was Australian, called Rutherford. So we jump to 1911 AD, and we find Rutherford. So this guy's experiment figures out that all positive charge in an atom, is concentrated in the center of the atom. Okay, of the atom. Electrons orbit this positively charged nucleus. Okay, there are no neutrons yet. Okay, no neutrons in Rutherford's theory. Okay, those came out later. They've discovered them later. Okay, so you have protons, maybe like that, in the center of a nucleus, orbited by, okay, here I have 4 protons, so I need 4 electrons, orbiting this Rutherford's atom. Okay, and this was the correct picture, almost the correct. I mean, we still needed neutrons and quantum mechanics, but he was on the right track and he won a Nobel Prize for that. He hired a postdoc, and a postdoc, for those of you who don't know, once you go on to get your PhD in physics or in other disciplines, then you're usually hired. One of the first jobs that you can get is to be hired as a postdoc, and you work with a big professor, usually a big name, and you keep doing research until you hopefully get into a professorship position. Okay, so he hired Bohr in 1913 AD. Niels Bohr. Okay, he hires Niels Bohr, who finds that who discovers the quantum model. Okay, quantum model of the atom. So this guy figures that electrons do orbit the nucleus, but in discrete levels, or quantized levels, as we say. Only jumps between these orbits are allowed. And what do we mean by that? So let's say we have hydrogen, which is easy. Okay, so we have a proton and we have an electron. So the electron can only exist in this orbit and maybe this orbit and maybe another orbit of over here. It cannot exist anywhere in between. Okay, that's not allowed. Okay, I'm gonna put an X there and I'm gonna delete it. Okay, and only when the electron gets energy through light, through heat, through whatever, it can only jump at the next level with that has an integer value 2, and then jump back by emitting a photon. Okay, or maybe it can jump to the n equals 3 level and then jump back to the ground level, or maybe it's here and it moves between there and then it goes back, etc. So this is what we mean by quantum, by the way. Quantum means discrete. So a quantized quantity is something that only takes on integer values. So 1, 2, 3, 4, 5, 6, 7, etc. Okay, this is what we mean by quantum. And kind of the last, I mean, this is an ongoing topic of research. I mean, nuclear physics is still an active research field, and so is particle physics. So the story does not end here, but for our purposes, we are going to stop with Heisenberg. In 1920, we have Heisenberg. Oops, there is no E there. Heisenberg. Not the Breaking Bad Heisenberg, the actual Heisenberg. German brilliant scientist. He discovered the uncertainty principle, and this is what we will write here. So, uncertainty principle. And what this tells you is that we don't really have orbits of electrons. So this picture by Bohr, which is sort of like the planetary model, in which you have, the sun in the center and then the planet orbiting around the sun. So his atom was more like that. You have the proton in the middle, the nucleus in the middle, and then electrons orbiting in circular orbits around the nucleus. So he discovered that this is not the complete picture because electrons form a cloud around the nucleus. So you have a cloud of electrons and an associated probability that the electron can be found somewhere in the cloud. And this was like the probabilistic interpretation of quantum mechanics, as they call it. I'm gonna try to draw a picture because maybe this is confusing. So you have your protons again, okay? And then this is what Bohr said, that electrons orbit in discrete orbitals like that. And then Heisenberg says that no, this is not a complete picture. Electrons actually are found anywhere in this space. So this is what we mean by cloud. Like a cloud is spread in space, right? So this is the picture of where the electron is, okay? So there is a probability that the electron is perhaps there, or there is a probability that the electron is there. Maybe there is actually a non-zero probability that the electron is here, very far away from this Bohr orbit, as it is called. So actually the electron does orbit in discrete energy levels, like Bohr said. It's just that Heisenberg added the probabilistic description that tells you that we cannot know for certainty that the electron is at that position, for example, okay? We can only know the probability that the electron is there. So there is a non-zero probability that the electron is over here, but that probability might be like 10 to the minus 40 or something. So practically there are no electrons here. Whereas if we are over here, the probability is maybe, I don't know, maybe 5%, okay? So this is it for the historical part of how we came to understand the atom and the nucleus and such. Now let's talk about the masses and sizes associated with the nucleus and the atom in general. So masses and sizes. So as we said, the atom consists of a tiny nucleus, which is found in the middle, okay? So these are my protons and these are my neutrons. So that's the nucleus in the center of the atom, and it has a size of about 10 to the minus 15 meters or 10 femtometers, okay? Now, around the nucleus, there are electrons orbiting this nucleus, and the size of the atom is about, so the radius of the atom, say, is about 10 to the negative 10 meters. For those of you who are going to study at the university, this is 10 angstrom, as they call it. Angstrom was a Swedish physicist studying atoms, so that's hence the name. Now, let's keep moving on. For protons, the charge is plus E, which is 1.6 times 10 to the negative 19 coulombs. The mass of a proton is 1.67 times 10 to the negative 27 kilos. For the neutron, the charge is 0, so no charge. The mass of the neutron is about the same as the mass of the proton, so I'm gonna write it here like this. So mass of the neutron is about the same as the mass of the proton. Now for the electron, the charge, so maybe we should write this as Q. So Q is 0 for the neutron. Q is minus E, so minus 1.6 times 10 to the negative 19 coulombs for the electron. The mass of the electron though is tiny, so mass is 9.1 times 10 to the negative 31 kilos. And if we divide the mass of the proton with the mass of the electron, we find 1836. So the proton and the neutron are about 2,000 times heavier than the electron. So the mass of the atom is mostly equal to the mass of the nucleus. Okay, so the electrons are tiny, they don't play an important role in the mass of the atom. Now let's go define how we write down an atom. Probably know this from chemistry. So if we have an element X, the mass number is A, the mass number is the number of protons and neutrons, and Z we write at the bottom left corner of the element symbol. So X is the element, and Z is the number of protons. Okay, so Z is the number of protons, A is the number of protons plus the number of neutrons, and N is the number of neutrons. It's not written anywhere, I'm just writing it for completeness. Okay, so for example, if we have helium 6, 2, this guy has 2 protons and 6 protons and neutrons. So it has 4 neutrons pretty much, okay? And protons and neutrons are also called nucleons, okay? So nucleons are protons or neutrons. Okay? Now another thing I want you to see is that notice that if we divide 10 to the negative 10, which is the size of the atom, over 10 to the negative 15, which is the size of the nucleus, we get 10 to the 5, so 100,000 times larger. So the atom is 100,000 times larger than the nucleus. And if the nucleus is a P, so if the nucleus had the size of a P, the atom will have the size of a stadium. So imagine a P in the center of the stadium, maybe in a football pitch, then the atom will be as large as the pitch itself, okay? So atoms are large. Another thing that is important to keep in mind is that atoms are mostly empty space. And why is that? Because as we saw, the electrons orbit really, really far out from the nucleus, okay? So they are far away, so most of the space between the nucleus and the electrons is empty, okay? Now, what's the purpose of the existence of neutrons? So why are they there? Neutrons help in binding, so in binding the nucleus. As we will see, I mean, if the nucleus was just protons, it was gonna explode, right? Because protons exert a repulsive force between them because they are positively charged. So what really keeps the nucleus from exploding? It's the strong force, okay? The strong force is what keeps the nucleus bound. The nucleus bound. It is an attractive force exerted between protons and protons, protons and neutrons, or neutrons and neutrons, okay? So when you bring them really close together, so it only acts at distances of about 10 to the negative 15 meters. So only within the nucleus this force is present. And it's about 100 times stronger than the Coulomb force. Okay? So what happens is that, okay, despite the repulsive force between protons due to the Coulomb force, because they're both positively charged, you have the strong force that is attractive, but only in small distances. So if a proton is, say, at some position in space and another proton is, say, 1 meter away from that proton, then this strong force is not going to act. The protons need to come really close together. So how close? About 10 to the minus 15 meters. That's when the strong force kicks in and it makes the protons attractive. Okay. And okay, so far these are some general remarks and material that you need to be aware of. So this is kind of like the big picture of what's going on with nuclear physics. Now let's go see and talk about the Rutherford experiment, okay? So this is important, and this is something that examiners ask a lot. So guys, please pay attention. So let's talk about the Rutherford scattering experiment. This was conducted sometime in 1911 by Geiger and Marsden. These guys were Rutherford's students, okay? So around 1911, Geiger and Marsden, who were students, students of Rutherford, performed an experiment where they set where they shot alpha particles towards a gold foil, thin gold foil, okay? So let's define what alpha particles are briefly. So alpha particles are helium-4 nuclei. Okay, so only the nucleus. So this thing, you have 2 protons and 2 neutrons. Okay, so this is an alpha particle. It's a decay product. We're gonna talk about decay, nuclear decay in Unit 5. So it's a decay product when unstable nuclei decay. So I'm being a little bit confusing today. I'm sorry, guys. So when we have radioactive decay, so some elements are really energetic. So to go to their ground state or to become stable, they eject alpha particles. Okay, so this is the source of alpha particles. So what they did was that, let me use a clean page. So let's say you have some alpha particle source. So what kind of source is that? An unstable nucleus, pretty much, okay? So you take usually heavy nuclei, like uranium-238, decays via alpha decay, or other heavy elements like that, emit alpha particles, okay? So you put a source somewhere and you find a way to accelerate maybe your sources and all your alpha particles once they exit the source. Also, this whole thing has to be in vacuum, because if you're not in a vacuum, the alpha particles will stop in air, okay? They stop really, really fast, like within 3 centimeters of air, your alpha particles will stop if they are not in vacuum. So you need vacuum, okay? No material. Vacuum means no material in some tube, for example, okay? So you have your alpha particles. Somehow you set up a vacuum, etc. And you have your gold foil. So let's make it yellow. Okay, so this is your gold foil. Hopefully it's visible. Okay, and you shoot these alpha particles. Okay, so remember that at that point they were still thinking that the atom was the same as Thomson said, so a plum pudding. Okay, so if you shoot alpha particles, you expect them to go through and maybe have some slight deflection like that. Okay, so something like that, but you mostly expect them to go through without deflection. Instead, these guys, and I'm sure it was a shock to their teacher, to their professor, instead these guys observed this thing going on. So by the way, they had actually, let me make some space for me. Okay, so they had a detector, and this detector was maybe a photographic plate. So you put photographic plates, and most of you guys probably don't know what photographic plates are. Back in the day when people took photographs, they had they used materials, I think phosphorus or something like that, that was very, very sensitive to light or any type of radiation. Okay, so you use that material to take pictures, to take photos. And they use these plates for experiments too, because radiation also interacts with these elements. So if something is going on, if something hits that plate, light, particles, whatever, you will see a spot. So these experiments were performed in darkness, okay? You need a dark place to do this experiment. Not dark as in evil, but dark room or something like that. So they put photographic plates around. I guess by accident, they didn't expect that. And they saw this weird phenomenon. They saw the alpha particles going in and then deflected in all sorts of angles, okay? Some particles even backscattered and they came back, okay? So, and by the way, this is the gold foil, okay? This was a shock at the time. So I'm pretty sure the professor in the beginning thought, these guys are crazy, they did something wrong, etc., okay? So according to what they knew about the atom and the nucleus and stuff like that back then, it was as much of a shock as shooting a piece of paper with a bullet and that bullet coming back and hitting you, okay? So this is something that was not expected at all, okay? And let me go show you a simulation. Before we see the simulation, which I hope you like, let's write this down actually, so you have it in the notes. So this is the expectation. This is the Thomson atom. Remember, it was supposed to be a pudding, a positively charged pudding with electrons like plums. So those are the electrons, okay? So you expect alpha particles to just go through like this, okay? Why is that? Because if this was the picture, then if an alpha particle is in that region that I wrote down with an X, it will be deflected at that position from maybe some protons that are over there, some charge actually, not protons, some positive charge over there, and then deflected by the same amount by this amount of charge on the other side. So pretty much these vertical components of the force will cancel and the alpha particles will travel in a straight line. the electrons will not deflect these alpha particles by too much because they are massive, right? So the electrons are not going to deflect it at all. So you expect your alpha particles to go through because only the component that points forward, the component of the force exerted by this positively charged pudding, only that component will survive and push the alpha particles through. So you expect almost no deflection. But the reality, though, as we know it today, is that you have a positively charged nucleus, which is massive. Okay, how massive? Almost as massive as the alpha particles, if not heavier. I mean, here we are talking about gold, and gold. I should know this. The atomic number of gold is 79. So yeah, it's much heavier than an alpha particle. Okay, so the alpha particle comes in and it gets deflected by a lot. Okay, sometimes it even backscatters like that. So this is the picture as we know it today. Okay, so let's go see the simulation. Guys, I'm gonna include the link in the description. If I don't, message me, like write in the comments, and I will make sure to fix it. So let's go see the plum pudding model. Okay, so the idea here is that we start shooting alpha particles with pressing that button there, okay, the blue button, and the yellow thing over there is the gold foil, and they show a zoomed area of what's going on. So this is what you expect. We can actually include traces. You can increase the speed of the alpha particles, okay? You can make them go fast, you can make them go slow, okay? And this is what you expect. Your alpha particles go through, no deflection. Why is that? Because the horizontal component of the force from the positive charge on the one side is going to cancel the horizontal component of the charge from the symmetrically opposite side. So only the vertical component survives. So therefore, the alpha particles keep going in a straight line. The red thing here is the positive charge. The electrons are shown as blue here, okay? The blue kind of like plums on the pudding, okay? And you can see the alpha particles. And the size of this thing is 10 to the 9, is of the order of magnitude of 10 to the minus 10 meters, which is the atomic scale, okay? So this is the expectation. Now let's go see the reality. Let's go talk about the Rutherford atom, okay? So here we have the atomic scale again, and I think you can change the scale as well here. So they have two scales you can select between, seeing what's going on at the nuclear level and seeing what's going on at the atomic level. So let's start with the nuclear level. Press the button so we have alpha particles coming in. Let's draw the traces and let's increase the speed because it's cool. By the way, you can also change the nucleus, okay? So here they have 79. 79 is gold, okay? 79 for protons. So you can increase the number of protons and neutrons and see what's gonna happen. So you see that you get a lot of backscattering. By the way, let's make this into a very light nucleus. So let's do okay, this can go down to 20 protons, which is calcium, okay? So you see that we don't get a lot of deflection because this is a light nucleus with not a lot of charge. But if we have a lot of charge, we get a lot of deflection, okay? So alpha particle scattering can also be used to probe nuclei, like to figure out what's going on, what kind of nuclei you have in a material. So anyway, let's go to the atomic scale and see what's going on here, okay? So you see how actually lots of alpha particles just go through because most of atoms is empty. Most of the area around atoms is empty space. So lots of alpha particles actually go through straight, but lots of them scatter at various angles, okay? Let's go make this a light nucleus again and see the difference. See, you don't get a lot of deflection for the alpha particles. But anyway, you can play with this simulation. It's really cool, I think. I love this simulation. So anyway, let's go back to the notes. Okay, we saw what the expectation was, and we saw what the reality actually is. Now, what are the key observations from these experiments and from the simulations we saw? So key observations and conclusions. And guys, this is really important. It's asked in 6-mark questions a lot, okay? So most particles, as we saw, most alpha particles go straight through without deflection. So theta is 0, okay? So this is the observation. What's the conclusion from this? Thus, atoms are mostly empty space. What's the second observation? Some alpha particles deflect by angles as small as about 10 degrees. This means there must be a positive nucleus in the center of atoms that deflects alpha particles, okay? And then the third observation is that a few particles deflect by theta larger than 90 degrees, okay? This means that the nucleus is extremely small with all its mass and charge concentrated in a small region in space. So atoms consist of positively charged nuclei. Okay, so this is not in your book as far as I know. So let's go talk about the distribution of alpha particles with respect to angle, okay? So when I write this WRT, it means with respect to. So what I mean by that is that I want us to plot. So if you have an incoming stream of alpha particles and they hit the nucleus, okay, something like this maybe, okay? I want us to see how many particles go through. Like if you start with 100 alpha particles, how many go straight through, how many deflect, and by an angle of say, okay, this is theta equal to 0, this is theta equal to 10, say, assume that, and maybe this is theta equal to 120 degrees, etc. So we go and plot this thing. So if you put the number of alpha particles in your y-axis and theta in degrees is your x-axis, and maybe this is 0 degrees, maybe this is 10 degrees, maybe this is 45 degrees, maybe this is 90, and maybe this is 180 degrees, then the plot is going to look like this. Most of your alpha particles go through, then as you move at larger angles, very few particles go through. So you see that most alpha particles, so if you start with 100, say, so this is the number of particles you start with, okay, almost all of them go through, and then some of them scatter by 10 degrees, very few of them scatter by 45 degrees, and by the time you come to 180 degrees, maybe one alpha particle deflects by that much, okay? So the overall conclusion from Rutherford's experiments is that using this experiment, they kind of found that so Rutherford's experiment found the planetary model of the atom. And by planetary, we mean that we have electrons orbiting the nucleus in circular motion. But there are no neutrons yet, okay? No neutrons yet. Let's talk about neutrons briefly. So the mystery back then was that they knew that the atom was heavier than what it should be if it only contained protons in the nucleus. So they knew that something was there, but they didn't know what it was. So neutrons. This is not required knowledge for A-level physics, but occasionally A-level examiners ask questions that require some knowledge. So it's good to know even optional things. So I'm gonna write this as optional, but it's good to know. So how were neutrons discovered? So first of all, they were discovered by Chadwick, I think in 1927, and his famous experiment. So let's digress a little bit and talk about nuclear reactions. So nuclear reaction. What is a nuclear reaction? It's similar to a chemical reaction, but here we have, instead of exchanging electrons like what's happening in chemistry, we exchange protons and neutrons. What do I mean by that? So if I send an alpha particle and make it hit a target containing beryllium-9, say, okay, beryllium-9, and beryllium has 4 protons. One possible reaction is that I might produce, if the speed of the alpha particles is high enough so that it comes close to beryllium and interact with it, I might produce carbon-12 plus 1 neutron, okay? And the way nuclear reactions work is that this is, if we break this into the before and after part, before and after. So the mass number before is, the total mass number is 4 plus 9, so 13. And the total number of protons is 2 plus 4, so 6. So whatever we have before must match whatever we have after in terms of protons and neutrons. So the mass number after is 12 plus 1, so 13. So this works. Total number of neutrons is, protons is 6 plus 0, right? So 6. So this works too, okay? All right, so how do we make this happen? So what did Chadwick do? So let's do the setup. So send alpha particles on a beryllium-9 target. Okay, so this is what he did. So 9 beryllium target. So he sends alpha particles, and this reaction takes place, okay? Some alpha particles merge with beryllium, they produce carbon, and they eject neutrons, okay? So you have neutrons coming out at all angles, okay? So they are all over the place. Now, neutrons are neutral. They have no electrical charge. They have no charge, okay? So how do you detect them? You make them collide with some target, okay? So it's sort of like the neutron is sort of like the cue ball in billiards. So you hit the cue ball against object balls, and then the object balls move. So the neutron here plays the role of the cue ball, and if we send this cue ball to a C2H4, which is paraffin target, okay, so this is a paraffin target. Paraffin is a material that has lots of hydrogen, so lots of protons, okay? So neutrons come in and they hit protons, okay? They hit protons out of this target. But protons are positively charged, so you can easily detect them using photographic plates, for example, or using any type of detectors, okay? Detectors usually detect positively charged, charged matter, okay? So using detector, and you see that lots of protons go through your detector. So you know that something kicked out these protons. So something kicked these protons out of your paraffin target. And what was that? It was the neutron, okay? Because, and how do you know that it was a neutron? You know that because most of the momentum of the neutron is transferred to the momentum of the proton. So neutron must be a massive particle. If it was not massive, it wouldn't be able to kick protons out, because it's like having a very small and a very small object ball, cue ball hitting a very heavy object ball. It will transfer no momentum. So you know that neutrons were massive, okay? So this is what Chadwick concluded, that neutrons are uncharged particles, but massive. And how do we know that? From the conservation of momentum, pretty much, okay? So the detection was possible. So detection relies on momentum conservation. And what's the situation here? Let's make this one-dimensional to make it easier. So you have a neutron traveling with velocity v. You have a proton which is not moving, and this is the situation before the collision and after the collision. You have a stationary neutron that stops in the material, so u is 0, and you have all the initial velocity transferred to the proton, okay? So neutrons were discovered pretty much just like that. So we have neutron discovery. Great. So now we have an atom that has positively charged protons in the middle and neutrons, okay? So mystery was solved, okay? So the next topic we're going to talk about is electrons from atoms. So how do we get electrons out of atoms, okay? Electrons from atoms. So atoms, have electrons orbiting their nuclei, right? there are nuclei in, as we saw, discrete energy levels. And this is the case in gases mostly, okay? So gases are dilute enough so that you can observe the discrete energy levels of atoms. So what I'm trying to say is that in solids, you don't really see discrete energy levels, but instead you see electronic bands. So atoms orbit these nuclei in discrete energy levels for gases, or electronic bands for solids. So let me draw the situation. So for example, in if you have helium-4, I don't know why I like helium-4 so much, but anyway, it serves its purpose here. So this is my helium-4 gas. So helium-4 gas, and because it's a gas, you can easily observe discrete energy levels. Okay, so what I'm trying to, so the values here are the energy of an electron in that discrete energy level, and the energy is in electron volts, and 1 electron volt is 1.6 times 10 to the negative 16 joules. So if you have an electron, it can jump to an excited level and come back. And if you give it enough energy, how much energy? An energy equal to 54.4 electron volts, it can actually escape. So electron escapes the atom. So you need a large amount of energy usually to make the electron escape. Now in solids, the picture in solids is that, for example, if you have sodium-23, so sodium-23, in solids solids have a lot of density. How dense are solids? They are about 1,000 times denser than gases, okay? So atoms are squeezed together in very, very neat closed spaces. So these are the electrons around these atoms, but because there are many atoms, you don't really get discrete energy levels anymore. You get bands, okay? What kind of bands? You have the valence band. Most electrons are here, and you have the conduction band, okay? So you have the conduction band up here, and you have a band gap between the valence band and the conduction band. This band gap is 0 for metals, okay? Because for metals, electrons are free to move around their atoms, whereas for insulators, electrons are not free to move around, so the band gap is huge for insulators. Okay, so the key point here is that you have to give the electron some energy to escape an atom, either in a gas or in a solid. So I'm gonna write this down. So energy is needed to extract electrons from atoms. In the case of the photoelectric effect, which you studied at the AES level, energy is provided from light. So you have a photon with energy h times its frequency. So this is the photon energy. The photoelectric effect is observed in metals, okay, so solids. So we are talking about something that has valence and conduction band like we discussed here, okay? So you have some incoming photon with some energy hf, so that energy should be equal to the work function, and the work function is the energy needed to extract one electron from the atom, and this work function is related to this valence and conduction bands. So don't confuse it with this picture here of the discrete energy levels. This only applies to atoms. I mean, this picture over here. Sorry, to gases. Whereas this picture is what applies to the photoelectric effect, okay? So every element has its own work function, okay? So the photon has to have enough energy to overcome this work function and extract an electron with some energy 1/2 mv squared, okay? Actually V max, okay? So this is the energy of the kinetic energy of electrons, of ejected electrons, okay? And just to give you an order of magnitude, phi is about 4 electron volts. And again, we said, we defined what 1 electron volt is. So what does 4 electron volts means? It means that you need a 4-volt battery to accelerate 1 electron at an energy of 4 electron volts, okay? Now, this is kind of like a review of AS level physics. So you learn about the photoelectric effect in your probably year 12. The last topic I want to talk about in this video is the thermionic emission. Of electrons from atom. So this is a phenomenon that it is observed. So observed in solids. So metals mostly, okay? And at temperatures that are really high. So how high? I'm gonna write here about 2000 degrees Celsius, okay? So really hot. Only electrons are emitted from this process. And this thermionic emission process resembles the photoelectric phenomenon that we discussed earlier. So in the photoelectric phenomenon, we have a photon giving energy to the electron and making it eject. Here, the heat is what makes electrons emitted from atoms, okay? And these electrons gain energy from heat, overcome the work function, and get ejected from atoms. Do I want to mention anything else here? Let me see. Yes. Y is heat energy because E is kT. Okay, this is the Boltzmann constant. So Boltzmann constant. So anything that has some temperature can be translated to energy. So temperature and energy are interrelated. This is something we will learn in Unit 5 and thermodynamics. So, but anyway, you don't need to know this. So I'm gonna erase it actually. So heat is energy pretty much, okay? And it makes electrons get ejected. So one application is the electron gun. This is one application of the thermionic emission of atoms. So how does this work? So let me draw the situation here. So this is the electron gun, okay? This is a screen. So the electron gun has a fluorescent screen, okay? And in this electron gun, you have you put some heating voltage that heats up this metal filament. So this is the heating voltage, which is about 5 to 10 volts. Okay, so this voltage provides heat to this. Let me use green, to this metal filament, which is usually tungsten. Okay, so this initial heating makes some electrons come out. Okay, so you have some electrons coming out of the tungsten. Then you can apply an accelerating potential, so an accelerating voltage. So let me use black again for it. So you can set up something that is called an anode, okay, and connect here an accelerating voltage. Okay, so this is the positive side, so this is positively charged, okay, and you can set up an accelerating voltage. And how much is this voltage? 100 to 5,000 volts, okay? So now this voltage attracts the electrons, okay, that pass through the anode and hit this fluorescent screen, okay? And this whole thing is in a vacuum, okay? So this is a vacuum. The whole thing is in a vacuum. Otherwise, the electrons will stop, okay? And this whole hole over here, sorry. So this hole in the anode is large enough so that electron diffraction phenomena are not observed. And electron diffraction phenomena are observed. So let me write this here. Electron diffraction. So electron diffraction phenomena or electron diffraction is observed when electrons pass through atoms, so through sizes of about 10 to the negative 10 meters. So if the hole is like 1 millimeter, you're not going to see electron diffraction. But if you put, so one thing you can do is that you can put maybe some material in that hole, maybe carbon, and then the electrons will pass through carbon and you will see diffraction phenomena, okay? But the electron gun is set up so that that hole does not allow for electron diffraction to happen. So let's go do a small calculation here related to the acceleration voltage. So if V with which we accelerate electrons is 5,000 volts, let's go see how much energy they gain, comma, the velocity of electrons can be calculated using conservation of energy, right? Calculated using conservation of energy. So 1/2 times the mass of the electron times its velocity squared should be equal to Q times V. What's the charge of one electron? E, right? So 1/2 the mass of the electron times V squared is equal to E times voltage. Actually, let me write this voltage with red so that it doesn't look the same as the velocity, okay? So V is simply the square root of 2 times E times the voltage over the mass of the electron. If we plug in values, actually I'm gonna run out of space, so let me move this here. Okay, so 2 times 1.6 times 10 to the negative 19 coulombs times the voltage, which is 5,000 volts, over 9.1 times 10 to the negative 11 kilograms. I don't need the units here because it works out to meters per second. Okay, oops. This gives me 4.19 times 10 to the 7 meters per second. That's really fast. That's like 1% the speed of light, 10% the speed of light, actually. Okay, about that. Now, so these electron guns give electrons a lot of energy. Okay, and the final, I think I said final for the thermionic emission, but the final topic I want to talk about here in this video is particle wave duality. Okay, which was pretty much confirmed using this all these discoveries we talked about today. So in 1924, I'm gonna call him Prince de Broglie because he came from an aristocratic family, suggests that much like light, which is a wave, behaves as a particle. So how do we know that? From the photoelectric effect. Then the electron, which is a particle, can behave as a wave. And this was just a hypothesis at the time, okay? And these electron waves should have a wavelength, because waves have a wavelength, right? And this wavelength was hypothesized to be equal to h over p by de Broglie. And h is Planck's constant. I'm gonna talk about it in a moment. And what is p? Mass times velocity, right? So de Broglie suggests this about electrons, and later this was generalized to all subatomic particles. And h is Planck's constant equal to 6.63 times 10 to the negative 34 joules times seconds, okay? And if you work these units out down to base units, you will find kilograms mass squared seconds to minus 1, okay? Now, if electrons are accelerated by a voltage of 100 volts, then their energy, then their energy will be E is equal to Q times V. The charge of the electron is E. Our voltage is 100 volts, so the electrons will have an energy of 100 electron volts, okay? Now recall that E is P squared over 2m. So this allows us to calculate the momentum of these electrons. So P is gonna be the square root of 2 times the mass of electron times the energy, which is 100 electron volts. If we plug everything in, we find 5.4 times 10 to the negative 24 kilograms times mass times seconds to the minus 1. Okay, so that's the momentum of an electron accelerated by a potential difference of 100 volts. So if we use Prince de Broglie's formula to find the wavelength of such electrons, we will find lambda is h over p. And if we do the calculations, we will find 1.2 times 10 to the negative 10 meters, which exactly matches the spacing between atoms in solids, okay? So in solids, the atom spacing is about 0.1 nanometers to 1 nanometers. So about 10 to the negative 10 meters, in other words, okay? So if we have salt, for example, salt is like a cube. So it looks like this, okay? Okay, something like this. Let's draw the chlorine, the Cl, the chlorine atoms with Cl. And okay, this is the sodium. So something like this, okay? And the distance between these atoms is about 10 to the negative 10 meters. Okay, so how do we know that electrons, how do we verify this theory by de Broglie? So if electrons are indeed waves, and if we make these electrons pass through this electron gun, remember the electron gun we talked about earlier? So if we make these electrons that are produced by the electron gun pass through, if we put a cube over there, okay, a small salt cube in the hole there, and make the electrons pass through that, we will see interference phenomena, right? Just like we do with waves. When waves pass through openings that have the same length as the wavelength of those waves, you see interference patterns and diffraction patterns, right? So you expect these electrons passing through a salt cube to have interference phenomena, okay? And this is what Davison and Germer proved in 1927. So they did an experiment to prove exactly that using electron guns, actually, okay? So I'm gonna write this down. So electrons with lambda of about 10 to the negative 10 meters will undergo interference phenomena and or diffraction if they pass through materials with spacing of 10 to the negative 10 meters. So Davison and Germer in 1927 proved that. And I think they won a Nobel Prize, and also de Broglie won a Nobel Prize for his theory. I know that de Broglie got a Nobel Prize for sure, and I think Davison and Germer got a Nobel Prize as well. So this is the whole picture now, okay? So you start with the thermionic emission, you accelerate particles in an electron gun, and you just see what's going on. But then if you put some solid material in the track through which electrons pass through, you will see interference phenomena, okay? And this is how the de Broglie theory that electrons are also waves was proved. And this is it for this video, guys.